My name is Nur Fadel. I'm working at CSCS. I'm working mainly on helping scientists improving their code, especially for PD simulation. And I'm currently working with Patsy, Trillinos, which are numerical libraries, and Kokkos. So now we'll start an introduction of Kokkos, what Kokkos is. And first of all, I will show you why I'm using Kokkos, why there is a big momentum about Kokkos, who is developing Kokkos, and then we'll dig a bit into the basic concepts of Kokkos. So basically the views, the concepts of execution, memory spaces, and finally the layout. And at the end of this lesson, I will draft the conclusion, and I will give you also additional information in order if you want to dig more about Kokkos. So, motivation. Kokkos is a C++ performance portability. The idea is that you write once one single source, and then you use on multiple architecture. So with Kokkos, you use C++, and it's been designed in order to use a descriptive programming model. It's able to compile code for CPUs and GPUs for multiple architecture, from standard CPUs to GPU like NVIDIA, CUDA, but also nowadays legacy architecture like kernel, BlueGene, and so on. So Kokkos is already for use. It's been established in 2012, so almost 9 years ago. It's been established in Sandia National Lab and is currently developed by 5 national labs in United States. I would say that probably is the most used library for heterogeneous parallelization in United States. Currently, there are more than 100 projects using Kokkos, and can compile with multiple compilers like GCC, Clang from GCC 5 and so on, and newer version, Clang 4 and newer version, NVCC, of course, in order to run on CUDA, but also IBM XL and also Intel compiler. So the Kokkos team is currently made by Berkeley, Sandia, Argonne, Los Alamos, and Oak Ridge, but also we had a small contribution by CSCS. The main developer is Trot, but there are many developers currently working in Kokkos. Kokkos was born as a part of the Trillinos, but then has been removed from Trillinon to make it more simpler to use and more general. So why Kokkos? Why we are using Kokkos? Mainly because there are in the current present, in the future there will be more architecture, more diversity, and therefore developers want to write once the code and being able to run on multiple hardware, but still run in an efficient way. There are other candidates above Kokkos. There is Raja, there are Occam, there is OpenMP 5, and probably the most mature among Raja and Occam and other library like Kokkos is definitely Kokkos. But there is still OpenMP target, probably you already heard. That will be for sure available in the new machine like the NERSC Permuter or the Frontier or Aurora or El Capitan. But still, there are 2 advantages of using Kokkos. Is that Kokkos can be installed also on older architectures and is already available, for example, on Summit and Sierra and Trinity. But at the same time, it's not clear how will be OpenMP interoperable among the different vendors, so among AMD, CUDA, and IBM. And above this, there are also CUDA, there is HIP, and the near future will be SQL. Already in standard laptops, Intel standard laptops, you can already use SQL, for example. So if you want to run also on this architecture, Probably the only solution currently that could run easily is Kokkos. So if you have already a code, there's been code written in C++, you already know that can be real painful to rewrite the code. If you take an industry estimate, a full-time software engineer writes 10 lines of production code per hour. That means that 20,000 lines of code per year. So if you have already an HPC production application, this roughly in the best cases, 300,000 lines of code. For example, Linux is 4,000 lines of codes, and similarly also Patsy. So considering a conservative estimate, you need to rewrite 10% of your application to switch programming model. This will end up in just switching programming model cost a lot, multiple person year per app. So this need to be considered now and in the future, since we will have multiple architecture, and also because it's not feasible from the economic point of view. So what is Kokkos? Kokkos is a C++ programming model for performance portability. I underline performance portability because there are other attempts to have portability, so have one code run everywhere. But with Kokkos, the design is focused on having a code that is performant on multiple architecture, probably not as the native implementation, but very close to the native implementation. So it's a C++ templated library on top of a few backends. Most common backend are OpenMP, CUDA, HEAP, and SQL. Also, there is OpenMP target. It has been designed in order to code in a descriptive way, not prescriptive way, and align with the developments of C++ standard. What I mean is that there are actively, the developer of Kokkos are actually working, pushing their implementation also into the C++ standard. The idea is that in the future, in the very long run, Kokkos will not exist anymore, but what is being coded, because what is implemented in Kokkos will be part of the C++ standard. And of course, it's open source. So in GitHub, you can find the Kokkos repository with the collection of the libraries of Kokkos, and also address common needs of modern science. So inside Kokkos, there are multiple libraries. Among them, there is also a math library that is currently developed for the needs of having vector and multidimensional and matrix vector. Tools also for profiling. As you know, when you write the code, then you need definitely to debug and to profile. And last but not least, also currently there are interfaces for Python and Fortran. And above all, also the documentation. So if we can describe Kokkos, Kokkos is at the heart of the system. So on one side, we have simulation, for example, wind turbine, CFD, molecular dynamics. For example, Lambdas is based on Kokkos. There is a Sierra Toolkit who is based on Kokkos, and LGA simulation. They are based their code on Kokkos. And Kokkos inside take care about the complexity of code of running the your simulation on multiple architectures. So it has backends for kernel, for AMD GPU, for CUDA, has backend for ARM, and a special optimization also for Xeon CPU. So the Kokkos ecosystem, as I say, Kokkos is not one library; it's a collection of libraries. The most important is if you can see my mouse, is Kokkos Core in the middle. Kokkos Core is the oldest library who has been developing Kokkos. And today I will show you I will explain some the basic concepts of Kokkos Core. And Kokkos Core let you run parallel execution and having, of course, parallel data structures on multiple architecture from CPU, so based on pthread or OpenMP, to GPU like CUDA or AMD. Then there are some auxiliary libraries who are useful for your computation. Among them, there is for sure the Kokkos tool on the left. Kokkos tools has the debugger, so you can debug. There is a special debugger for the routines of Kokkos, and also the profiler. Once you run your code runs fine, but there are some problems. So it's too slow in certain cases. You can profile and check if there are, certain weights or your unnecessary copies. With this, with Kokkos tools, it's very easy to profile and then tune. Then there are Kokkos kernel. As I mentioned, Kokkos kernel is basically the math library of Kokkos. It's barely new. It's been started developing 2 years ago. It has linear algebra kernels like BLAS and LAPAC. Has some algorithm for sparse linear algebra, and has also graph kernels. It's still, I would say, probably the most active library developed right now is Kokkos kernel, and in the future will be for sure other feature will be added to Kokkos kernel. About this, there is also Kokkos remote spaces. Also, this one is pretty new. So this library has been built in order to have PGAS MPI in Kokkos, because Kokkos has been designed mainly for MPI for intranode parallelization, and this library is meant for internode parallelization. Above this, there is Kokkos support. Part of this the presentation is you will find also in the Kokkos support, where we have documentation, the wiki. We have tutorial. Later, I will show you in the next slide some links if you are interested in additional advanced feature of Kokkos. And there is also a Slack community where you can ask easily support. Last but not least, there are from time to time before the pandemic, actually, we'll see after the pandemic if they are going to organize again boot camps, so meetings where you can meet with the developers and learn how to use Kokkos. There have been a few in the United States, there's been ones also in Europe. So if you are interested also in Europe, probably in the future will be other boot camps. So Kokkos ecosystem is addressing, as I said, multi-core, mini-core, and CPU plus GPU, and also APU. Currently, there is no plans to support FPGA. If in the future will be supercomputers with FPGA, probably will also will be added also the backend to FPGA. So, as I said, additional tools, there are Kokkos kernels based on BLAS, LAPAC library and graph library. Kokkos remote spaces is internode parallelization. Kokkos profiler and debugger are meant for debugging and profiling. And last, the Kokkos tutorial, where there is the documentation, very rich documentation about Kokkos. So, as I said, Kokkos, the idea of Kokkos is to support the scientific community, and once they develop something, they try to push to the C++ standard. So everything, you shouldn't be worried of being tightened to Kokkos forever, because the idea is that soon the community, so the C++ committee, accept the one feature from Kokkos will be integrated in the C++ standard. At the same time, the Kokkos developer, they will port the accepted feature to legacy version. And last but not least, there are more than 10 people from Kokkos team, currently Kokkos developer or a former Kokkos developer who are part of the C++ standard committee. So the message I would say is that it's not Kokkos an additional library that will sorry, I've read just now the one question from Eva. I can answer where the book camps are usually announced on the Kokkos webpage. No, will be on the Slack. So if you want to be updated about Kokkos, I do recommend to subscribe to Slack. In the next slide, I will also post the link to the Slack channel. And yeah, we're saying that there are more than 10 people working with the C++ standard community. So don't worry if you're going to use Kokkos. The idea is that the data structure, the concept of Kokkos will sooner or later end in the C++ standard. I will show you one example. Is in C++ 23, standard MD span. So I know C++ 23 is not yet the standard, but will end up this multi-dimensional span. So as you know, C++ doesn't have multi-dimensional arrays like Fortran, MATLAB, Python, and probably the only one who doesn't have them is C++. And this problem will be fixed probably in C++ 23, where will be introduced MD span. They basically are the Kokkos view that I'm going to explain later. So are multi-dimensional arrays. So benefit of this is multi-dimensional, of course. Data layouts allow adapting hardware to specific access pattern. This is very important to have a performance portable implementation to avoid basically cache misses. It supports also sub-views, like for example Python. It has a reference semantics, so you can track of the memory and you don't have to deallocate it. And a very nice feature is also possible to have array which are defined a compile time and a runtime. One example, this is how you write a view currently. We will see, will probably slightly change the syntax in C++, but basically, don't worry if you don't understand now. I will show you later and in other slides what are views. But basically here we are saying that we have a three-dimensional object where there are these two stars means they are defined at runtime. And this 5 means the third dimension is defined at compile time. And layout left, you will see later. Layout, basically, we define how to access the memory. So before digging into the main concepts, I will tell you a few recipes in order to compile the build. The Kokkos GitHub is this one, so github.com/kokkos/kokkos. You basically clone this. You can configure. There are two ways to compile install. Configure with CMake. Already with the standard laptop running CMake will automatically find almost everything. Will detect automatically that you have OpenMP, so you can run Kokkos serially and with OpenMP. And in case you want to use CUDA, you have to specify where the CUDA library are, and then you have to make install. The easiest way, although this is not so difficult, the easiest way to use Spark. So you simply do Spark install Kokkos plus OpenMP means that you are enabling OpenMP. This is pretty redundant. On a standard computer will by default detect that there is OpenMP and will enable OpenMP by default. Compiling everything from scratch will take a while, but I mean it's super easy because with one line you compile Kokkos, you can run. So let's move on. As I said, the online resources are the following. So as I say, GitHub for Kokkos. Then there is still under GitHub, under Wiki, there is the complete API reference. As I mentioned, the Slack channel is kokkosteam.slack.com, and I definitely recommend to subscribe to the Slack, because if you have any question, they will answer in less than 1 hour. And there are also the communication about the new version, the new release, the new bootcamp, and so on. It's the most updated place for having news about Kokkos. And last, additional tutorials. Still in Kokkos, there is in the Kokkos repository, there is this Kokkos tutorial. Kokkos tutorial. And inside there are all the slides, of every presentation that the Kokkos developer did it in the last 10 years. There are lots of examples, lots of exercises. In any case, if you want to learn more. So let's move on to the basic concepts. I would like now to address some concepts that were crucial for Kokkos. The idea at the end of this presentation, you will have the basic tool to write some basic Kokkos code. And of course, there are much more functionalities in Kokkos which are important, but not crucial, let's say. So you can run a simple computation with that. So basic compatibility that I'm going to explain are a simple 1D data parallel computation patterns. So which are the parallel patterns, the easiest one that you are going to use with Kokkos. Then we'll decide where the code is run and where data is placed. This is very important since we are trying to address multiple architecture. And then managing data access pattern for performance portability. This will be the last topic. It's very, very important for have performance portability. So to address again about performance portability, the idea is we have one implementation that runs on multiple architecture and obtains the idea to obtain performance memory asset patterns across architecture. And this can leverage an architecture-specific feature whenever is possible. For example, is that if you ever use locks, locks works fine on CPUs. If you're using lots of locks on GPUs, will not scale for sure. So, for example, in Kokkos, there are no locks at all. So the idea is to use functionalities that you can use everywhere that can be scalable. And try to match as much as possible the memory asset pattern of the architecture that you are going to use. So first, some names. Let's consider one example. This example is a loop, basic loop. I copy paste this from a finite element code, where we looping over the elements, and here in the body we are calculating the quadrature rule. Can be anything, but let's start with the loop. This is a serial one, and we call for clarity that our pattern is the for loop. The execution policy, so how the things are executed, is this iterator. So that will start from 0, will iterate until num elements, so the total number of my finite elements, and will increase by one. And then there is the third part, which is this computational body, so the actual part that we want to parallelize. And what we can say that pattern, so for and execution policy drive the computational body. So we decide where and when to calculate what is in the computational body by the for, so by the pattern, and by this iterator. So let's see with OpenMP. With OpenMP, you have this parallel, so you have the parallel for. You basically, it's very simple. You add a pragma. And the main difference is here you are defined as a parallel for, and basically it remains the same. There are other ways to parallelize above OpenMP. This is simple. There is OpenACC, OpenMP target, OpenCL. And well, now we are going to see how we do on Kokkos. So the idea before showing how we do in Kokkos is that the standard thread parallel programming model may give you a portable parallel execution. And this is supporting on the target architecture, of course. But how about the performance? This is very important, the computation memory assets pattern. So how we assess the memory. So for Kokkos, you have to give an iteration range, a computational body. So as I said, the red one is the computational body and iteration range. And Kokkos maps work to execution resources. Iteration of the computational body is a unit of work. So each one of these loop is a unit of work. The iteration index identifies a particular unit of work, and the iteration range defines the total amount of work. So how we can assess, give to this body of work to Kokkos? Through functors. You have seen in the past what are functors, but to recap, a functor is a class with the function. And what we do is with Kokkos is the following. So we have the parallel pattern. Then Kokkos is still a 4, so it's a parallel 4, like in OpenMP. And this is this parallel 4. So we write Kokkos common parallel underscore 4. Then we have the our iterator, which is the number of iteration, and then the body, the actual activity we want to parallelize, we pass through a functor. So through a function who has a function. Parallel functor body must have access to all the data it needs through the functor's data members. This seems obvious, but once you start coding, you realize that not obvious, because of course you have your functor, but once you pass in to the parallel 4, everything should be, the data the functor needs should be already inside. And, we'll see a bit later. And above the functor, there are other ways to pass data, which are the lambdas. Lambdas are 99% of the cases, the system we pass data to a generic Kokkos parallel pattern, in this case, a parallel 4. Why? Because lambda are concise, are very easy to understand, and much less verbose than a functor. So you don't have to write the class, the constructor, copy constructor, and so on. Basically, the lambdas, with lambdas is the compiler that's auto-generating a functor for you from the lambda. So the snippet code means is all we have already data from before. In this case, we can have the atom forces. We have already some data. Then still we have this parallel 4. Then we have the iteration number, which is in this case the number of atoms. And then we pass the lambda. The lambda, there are two important things. One is the index. Then we have to pass to the lambda. And there is also this equal. This is very important. We need to capture lambda by value. Why? Because otherwise it will not work on GPUs. So if we want to run everywhere, our idea to run everywhere, we need to capture by value. You can try, for example, to capture by reference. You can run on CPUs. So if you run OpenMP, it will run without problem. But if you run the same code on GPUs, it will crash because will not have access to the data. So definitely we need to have this equal. So we need to capture by value. And therefore you don't capture containers by value because it will copy the entire container. So if we compare the three versions, so we have the serial we have seen before, OpenMP, where we simply add the pragma for a simple case, and then Kokkos. As you see, Kokkos usage is no more conceptually difficult compared to OpenMP. Basically, the annotation is just slightly different. So instead of have OpenMP this line, you have a different name for 4, and the iteration is the first value. Then the second argument is the lambda, captured by value. So let's take another example. So we have seen a parallel 4 let's see a slightly more difficult example. Let's do this integration. So a Riemann-sum-style numerical integration is probably, it seems the same. So you have a global value, the total integral. You have a for loop where you loop over the integral of the over the intervals of your integral, and you calculate all the sum, and then basically at the end you sum up what happened, sum up in the variable total integral. How we parallelize this? One option would be in this way. So we substitute 4 with parallel 4, we have the number of integral, and then we have the body of work. Unfortunately, with this, with the Lambda, unfortunately, this not work, will not compile, because basically we don't have, as I said before with the functor, we don't have access to total integral. Integral is outside. So there is a trick that you can use, for example, pointers, but nevertheless, in this case, you could have a race condition. So what we can do for solve this problem? And basically, there are there is one basic problem is the pattern. So we have used parallel 4. Parallel 4 is not the best option in this case, but there is a reduction. So we have to use a different pattern. This pattern is reduction, they probably seen before, where reduction combines the result of the contribute what has been calculated before by parallel work. So again, we can see 2 examples with OpenMP and with Kokkos, where we use this different parallel pattern. Basically, well, the main difference is that we have additional value where, variable where we can store what we are going to collect from the various threads. So with Kokkos means that we have parallel, not anymore parallel 4, but parallel reduce. We still have our index. We have the functor of the lambda and an initial value, which is the final reduce value, which is the global value, which is outside, and we can pass to the parallel reduce. And the lambda, if you see, if we look at the lambda, we have 2, in this case, values. One is the index, like before, but also this double value to update, which is a thread private value that is managed by Kokkos to calculate in each thread the partial value, and then Kokkos will sum up in the total integral. As I said, value to update is not the final reduced value. The final reduced value is total integral. Among Kokkos, there are other type of reduce. There are multiple reduce. This functionality is pretty new. It has been released last year. So you can have multiple reduce and basically have multiple arguments after total integral. And this way you can have different type of reduction. In this case, a reduction is the summation of result of each thread. You can have, for example, the summation and the max among the result of each thread. There are multiple type of reduction: max, min. Min loc means that you are receiving the minimum and the locality, so which thread has the minimum, the max loc. There are also booleans, and but I would say that in most cases, well, the most useful is the summation, the reduction of the summation. So let's now go and dig into the views. So view, why we are going to have view? We need a way to store in data multidimensional arrays, which can be communicated to an accelerator. And for this reason, we use views. Views are a lightweight C++ class with a pointer to array data and a little metadata. So we can see slightly like smart pointers. It's templated on the data type and are like, as I said, are like a smart pointer. So copy them, you can copy in your functors. So there are no problem of copying in your parallel pattern. And I showed before is view is templatized. In this case, the type is double. And depending on the number of argument, you decide also the dimension. And the idea is in this way. So you created your view. The view is not instantiated until you use it. And then you have your parallel for example, in this case, we have this DuckSpy where we iterate over n and we pass the view, so x and y, to our lambda. The view are captured by value. And one thing I haven't said before, every function in Kokkos can have a tag, can have a name. I do recommend to add these strings, in this case DuckSpy, because it's very useful for tuning and for debugging. So when you use the Kokkos debugger, you will see in the trace this name that you can give here. Are optional, but I do recommend to add in any case. So view can be a multi-dimensional array of 0 or more dimension. The number of dimension is fixed at compile time, so and there is no way to decide at runtime the number of dimension, but the size of the dimension can be set up at compile time or at runtime. Access the elements, you can access a single element via the bracket operator. And as I say, the allocation happen only when explicitly specified. So there are no hidden allocation. And copy constructor and assignment are shallow, so it means they are like pointers. You are not, when you are doing copy constructor or assignment, you are not copying the entire data, but you are copying the pointer. So you can pass by value, but not for reference. Reference counting is used for automatic deallocation. As I mentioned before, nice thing about views is the reference counting. So you don't have problem about deallocation. And basically are behaving like shared pointer. Example. So in the first case, when we have this star are not pointers, the developer decided in this way to address a three-dimensional view. In this case, there is going to be decided the size at runtime. In this case, the second one, so view double star star and 2, the third dimension is decided at compile time, while the other two dimensions, the first and the second, are decided at runtime. Third case, we have a view where we have the first dimension, which is decided at runtime. So when we run the constructor, we must give the n0, while the other two dimensions are defined at compile time. Last, of course, last case, you can have a view, three-dimensional view in this case, who has all the three dimensions decided at compile time. How can I access, as I say, with the bracket? So data, so our view is called data, and yjk, you can assign one value, one double. Runtime size dimension must come first. This is a limitation due to C++ currently, probably in the next version will not be anymore, but you must always give the runtime dimension before. So the dimension who are decided at runtime must be before. Some example. So, so many people has answered. before answering, here I have an example, so I hope that no one is sleeping. This example is a view. So first of all, we create a view of double with 2 dimensions. One is decided at runtime and one is decided at compile time. We create 2 views, A and B. And we give for A, we'll have 1 dimension will be n, and the second dimension will be 5. And B will have a k dimension, and the second dimension will be 5. Then we do A equal B, and then we create another view. This view in this time has 2 dimensions decided at runtime. And we initialize with B. Then we put A02 equal 1, B is 02 equal 2, and C02 equal 3. And we print the value ADA02. In chat, what value do you expect will have A? Good, great. So, yeah, you're right. So it's 3, because basically you understand. So this data we are referring to the same data. So the metadata of the view A, B, and C are pointing to the same exact data. So let's move on to execution and memory spaces. So we have seen the this is the parallel patterns, so for and reduction. I mentioned there are other type of reduction. We have seen some how to give work to these parallel patterns. We have seen how to give the data to these patterns, so through views. And now we see other 2 concepts which are crucial: execution and memory spaces. So execution spaces. What are? Execution space is a homogeneous set of cores and an execution mechanism. Basically, is through execution spaces, you assess for example, on CPUs, the core of your CPU, or in GPU, your accelerator. Among the example regarding execution spaces are serial. So with serial, so Kokkos serial, you will have 1 core. You have also Kokkos threads, will give you access to P threads on the CPU. Then there is Kokkos OpenMP, Kokkos Kugeda, Kokkos heap. There is also OpenMP target, and lately also Kokkos SQL. So how we are going to use the execution space? Let's consider code where you have also MPI, and you have this MPI reduce. You read some data from file, you run your stuff, and this is on the host. Then you have your parallel pattern, so Kokkos parallel 4, and you run over a number of somethings. And then you have the lambda, and you want to run this part. So I cannot hear anything. Is that only me? Guys, can you hear me? Okay.
Yes, we can hear.
Okay, perfect. So I will continue. The body of this parallel 4 that we want to parallelize. So first of all, the red part, so the host code, will run always in the host process. The parallel code can be run on different execution spaces. So want to do is to run on different execution spaces the parallel part, and by default will run on the default execution space. And how we can change this default execution space? There are 2 ways. One is, okay, rejoin. One is modifying Kokkos. So when you compile Kokkos, you can decide which is the default execution space. If you compile on your computer, by default, it probably will find OpenMP and will default to Kokkos OpenMP. But of course, it's not the only way. there are you can specify an execution space in the policy. So the policy in previous case was this value, so this iterator. In this case, on this slide is number of something. But now we will see that you can, even if you have a default execution space, it's, I don't know, OpenMP, you can specify different execution space and, for example, run on CUDA. So, and these are the examples. So below we have the classical, let's say, parallel for that we have seen, before the, sorry, in the upper part, we have the classical one where you have the parallel for with the label, the number of intervals, so our policy, and then the lambda. But actually this, if we want to see in detail, is actually not number of intervals, but behind there is this range policy who has a template. In this case, we didn't fill in the template, and therefore is using the standard range policy. But looking at the second example, you can use a range policy with a specific template. So what you do is you write range policy execution space, can be Kokkos CUDA execution space, and you pass the number of intervals. So in this way, we are saying to Kokkos, please run your Lambda function in this execution space. There are some additional features. We have to say something more to run this. There are some additional points that we have to clarify. Range policy takes a template argument, as I said. It's a policy that says I'm parallelizing over a set of intervals, where the set of intervals is a number of intervals. And we can decide this execution space only, and stress only at compile time. So you can decide to run on different execution space, can be serial, OpenMP, can be on GPU, but you have to decide at compile time only. The requirements for having this, you have to, first of all, it's obvious, but it's not always obvious. You have to compile Kokkos with the execution space enabled. Some of them are by default enabled. For example, Kokkos serials and Kokkos OpenMP is always enabled. But if you want to run on CUDA, that means you have to enable at when you compile Kokkos, and that means you have to also link to CUDA. Otherwise, you will not be able to use Kokkos CUDA. Another point is the execution spaces must be initialized. I haven't mentioned, but basically the Kokkos code must be encapsulated between two functions, which is Kokkos initialized and Kokkos finalized. Barely more or less like MPI. So if you have an MPI code, you should have MPI initialized, then Kokkos initialized, then you have all the Kokkos stuff that you want, then you have Kokkos finalized, and then MPI finalized. But more important, functions and functors actually, and lambdas must be marked with a macro for non-CPU spaces. Why? Now I will show you the lambda must be marked because otherwise the compiler doesn't know that this lambda must be run on your device. So if you have a code that's running on OpenMP on CPU, actually there is no problem. But if you run CUDA, you have to tell to the compiler saying, hey guys, this lambda must be run on the GPU. So how we can tackle this problem that we would like to have the same code for OpenMP and for CUDA, and of course also for the other execution space. So Kokkos provide these two macros, Kokkos lambda, Kokkos inline function. Kokkos inline function is for functors, Kokkos lambda is for lambda. I'm showing only lambda because it's much easier to see. It's the Kokkos inline function is basically the same. So it's a macro. So if you see my pointer, you define this Kokkos lambda. In case of CPU, so in case you are going to use, for example, OpenMP, will not do anything. Will only define this by value. But in case you are going to use the GPU like CUDA, will define and will add device host. So the point is, we are going to have the Kokkos parallel 4 with the label, with our range policy, and then the lambda. The lambda will be encapsulated inside this macro. So in this way, the compiler will know that you want to, in case you are going to run with heap or with CUDA, the compiler knows that this lambda must be compiled and run on the GPU. So we have seen how we can use GPUs and CPUs, but where is the data? So actual data, where we store the data. This is another problem. It's very important, probably even more important, because how you manage the memory is you affect greatly the performance. So you can use GPU memory, CPU memory, both. How? And for this, we have, after execution spaces, we have memory spaces. So there are other concepts that I'm going to tell you. So memory spaces are explicit manageable memory resources. In few words, where you put the data. So it can be the cache on your CPU, can be the on-package memory in your accelerator, can be your DRAM, can be also non-volatile RAM. Basically, the RAM that you can address from your code. So memory spaces. Every view stores its data in a memory space set a compile time. So I'll show you how to write a view. Actually, there is an additional template parameter that I haven't mentioned before that has in case you don't mention, the view will use the default one. So every time you use a view, you are actually using also a memory space. In most cases, you don't need to define a memory space, but in certain cases, it's useful to address. So which are the memory spaces available? There is the host space, and then there are others like CUDA space, CUDA UVM space, which is completely different from CUDA. There is heap space, and they have a SQL space. Each execution space has a default memory space, as I said, and which is used if space provided is actually an execution space. If no space is provided, the view data resides in the default memory space of the default execution space. So if you specify, we are going to use that one. If you don't specify, you will use the default one. In Kokkos, everything has been designed that the default is the smartest option. So don't worry, in most cases, you don't need to specify the default memory space or the default execution space. So this is the view we have seen before. This is the view with the template, additional template parameter. Basically, we have this addition default execution space column memory space, where we can decide where we want to put the data. Before going on, if you don't put anything, the Kokkos will use the smartest memory space for that type of view. If you are going to specify, you have to be careful because you can screw up everything, because you can, for example, create a view on the CPU, for example, force of using the CUDA memory space. And of course, in this way, you will have troubles. So let's see some examples. So let's consider host, so the CPU and the GPU. In this case, we create a host view. So we have a view which has two values. So it's a view of doubles with 2 dimensions. And we decide the CUDA space as a memory space. So what we do is we create no, there is one problem. Sorry, guys, there is one bug in the slide. Is actually missing the, okay, I will show you. Let's consider the first case. You have a view template type with double. Here is wrong, the template is host paste. And what will happen is that you are creating the data in the host, and the metadata will be still in the host. It's not written here, I don't know why it doesn't show in the slide. Then there is another, we now show another view, which is this code is related to the picture below. So we create a CUDA space, CUDA view where we templatize with CUDA space. So we have a view that is resident in the metadata is still on the CPU, but since we have decided CUDA space, since we have decided to have, sorry, since we have decided to have CUDA space, the data, the actual data is resident on the GPU, not on the CPU. Well, the metadata are still in the CPU. Ah, okay. Sorry, it was the. So sorry for mess up the slide, but basically, as I said, when we define host space, the data is in the host, so in the CPU. Once we decide for CUDA space, the data is on the GPU. The metadata is always on the host. So the anatomy of a kernel launch is we declare our views, then we instantiate our functors with the view. Then we have, we launch the parallel something, so parallel for, parallel reduce. And in this case, the functor is copied to the device, not before. The kernel is run, and then we copy the functor on the device, the copy on the device is released. There are no deep copies of array data, and views, as I said, are like pointers. So in a second example, we can have two views, one on the device, one on the host. So the device, here we declare the two views. Then we have the parallel for only when, and this is the case. So the first example, so we have the dev is on the device. So the metadata is still on the CPU, but the data is created directly on the GPU. While the host, the metadata is on the host, and the metadata and data are both on the host. When we run the computation, so we have the parallel for. In this case, we have that the metadata are copied to the GPU. So in case of the device, the metadata are copied on the RAM of the GPU, so you can run. But also the host, the metadata are copied on the GPU in this case. Of course, I'm addressing CUDA space where we are running on a CUDA space. What the problem with this application, so with this example, is that, as you probably see, the metadata of the host is on the GPU, is trying to address the memory on the CPU, which is forbidden. So we'll crash this example. So if we comment this host, we have only the device will run, but the host, this part will crash. In order to have this case, so we would like to have both, there is a spatial view. So now I'm going to show you a spatial view in order to address this problem. This view is called mirror view. Basically, you are mirroring between GPU and CPU. So first, as before, you create your view here. And then you create a host view. Host view is the type of host mirror. It's and with Kokkos create mirror view, passing obviously the view, is creating this host view. In this way, you can mirror between the two memories, and you don't have any more problem of accessing data from the CPU. Other way to do this is with CUDA UVM. The CUDA UVM, in this case, for example, is very useful when you're using CUDA space. In case of you're going to use CUDA UVM, you don't have this problem because you have a virtual shared memory, but has a drawback that the CUDA UVM is not always performant, and sometimes the performance decreases a lot. Depends how do you assess it. While with mirror view, you avoid the CUDA UVM. You can assess both data and keeping the performance at the high level. So how can I work with mirrors? I create a view array in some memory space. So as I show you, you have this view. Then you create your host view as the passing the view that you want to mirror. Then copying data back and forth is up to you. Kokkos is not automatically addressing the fact that you see is not able to check if you are modifying the data on the host and then copy on the device. It's up to you to decide when copy the data on the host and on the GPU. So you have to populate the host view on the host. Then you have to deep copy the host view to the view arrays. And here is deep copying is the actual copy, so the real copy. And then you can launch the kernel, as you see, we have seen before. And if needed, so when you have finished the calculation, so you run your parallel pattern on your device, you can do another deep copy from the device to the host. Why we are Kokkos force the user to copy manually? Because basically in this way you have idea what is going on your data, because otherwise you can have memory corruption. And another point is forcing you to have explicit deep copies. And this is crucial for performance, because in this way, you know exactly when you are copying a lot of data. So a shallow copy, it's pretty cheap because you are copy pointer. But in this way, you know when you are deep copying. And okay, probably we have mentioned about working on GPUs, but what happened in case I'm using the mirror on a CPU? I think, what happened? I'm going to have deep copy also on the CPU, considering that the view mirror is fully on the CPU, on the host? No, because when you use create mirror view, as we showed before, this allocates data only if the host process can access view data. Otherwise, host view reference to the same data. So when you have a code that is using mirror view with the device, like GPU, CUDA, there is no problem, we'll copy. While if you're the same code, for example, you compile and you run on OpenMP, automatically Kokkos is able to understand that you don't have to do a deep copy, and therefore will create a shallow copy pointer, and therefore you will not lose performance. There is a function, honestly I never used, but Kokkos give you this possibility to create a mirror. So create mirror always allocates data. So if you want, you really want to have a deep copy even on a CPU, you can have it with create mirror. Reminder, Kokkos never perform a hidden copy. So you have to address, so really have deep copy in order, write deep copy in order to copy back and forth the entire data. Otherwise, Kokkos is trying to, as much as possible to copy pointers. So, okay. Okay, I think sorry. Last concept I want to mention here is layouts. Then, which is the latest concept I want to discuss, which is really crucial, and it's a basic and concept that you must know to use Kokkos. So, layouts, as I mean, its generic name, you probably know already. Layout is the mapping of the multi-index to memory. So in memory, the memory is actually 1D object. And in case of the 2D, as shown in the picture, we addressing by rows or by column. If you have layout left in 2D, means you have a column major order, or if you are going to use layout right, you are going to have a row major indexing. This is crucial for performance. So how you use layout affect greatly the performance. I would say 90% of the performance come from this decision with Kokkos. And also the reason why the layout concept is the key concept that led Kokkos to be performant, and I would say more performant than OpenCL and other paradigms. So in Kokkos, there is an additional template parameter called layout, and you can have multiple options. The most common are layout left and layout right. So with Vue, we have seen the first template parameter. In this case, it's templatized with doubles. It's a three-dimensional view decided at runtime. We have the space we have just discussed, and then we have this additional parameter, which is layout. If you don't specify, as before, we'll use the default layout parameter. And I already said that if you use the default one, in most cases will be the best match for your application. But in case you can also specify the layout or use additional one. There are some specific one. Also, among layout left and layout right, you can also specify your layouts. So you can have your layout stride, layout tiled. You can write your layout, are basically 50 lines of codes to add a new layout. So layout left is the leftmost index. And most common layouts, as I say, there's layout left and layout right. And the leftmost index is stride 1, while for layout right, it's the rightmost index is stride 1. Which are the default memory spaces for CUDA space and host space? For CUDA space is layout left, while for host space and OpenMP space is layout right. Also for heap space, so basically for the accelerator spaces, is the default is layout left. So I bring this picture because this is an example of test case of Kokkos on multiple architecture. You can see this has been published in the past by the Kokkos developers and give you a clear understanding why layout is so crucial. So the black lines are a simulation on Hanswell using the two layouts. So the same code. In one case, you are using the -1, the left layout, and the solid one is the right layout. The same with kernel, and then the same with Pascal 60, so with the GPU. In both cases, you see that changing the layout dramatically change the performance. Basically, because you are going to have a lot of cache misses, and you're wasting your CPU or your GPU waiting for the data to retrieve the data. And especially in case of Pascal, so for GPU is even more dramatic. You see the difference is reached 10 times the, sorry, I lost. Okay, 10 times the performance. So it's really important to use the correct one. Okay. So if we have a deeper look at the layout in the CPU and the GPU, both are using threads, but in one case, so in CPU, you have only few threads, few cores with separate caches. So you don't need to synchronize the single threads. And the best way to perform is to do caching. While with GPU, you have tons of threads, and many of them must be synchronized with the shared cache. So the idea is where is the mouse? You want to read the one line cache with all of them in order to coalesce all of them. So the two big difference is that in one case you want cache, in another case you want to coalesce. The reason why we are using different layouts. I haven't mentioned what are the layouts, how, I mean, basically in the code of Kokkos, what does it mean having a layout? Basically, the idea is to give the right index in order to avoid cache misses. And on GPUs, we want to coalesce all the threads. And in CPUs, we want to cache all the threads. And CPU threads, as I said, are independent. Threads may be executed at any time, while the GPU threads execute synchronized. So threads must be running groups and execute instruction together. So in particular, all threads in a group or waveform must be finished their loads before any threads can move on. Okay. So I'm going to finish, so I will, okay. For performance, the access to view in the host space must be cached, while then the access to the view in CUDA space must be coalesced. So as I said, caching, if thread's current access is position I, thread's next access should be a position I+1, while correlation means if the current access is a position I, the thread must be T+1, current access should be a position I+1. So if you don't cache, probably you lose performance on CPU, but it's not, it's bad, but not so bad. If you are accessing GPUs in an uncoalesced way, the non-cache loads on CPUs greatly reduce the performance. It can be even 10 times lower. So in this way, it means that for OpenMP is cached and for CUDA coalesced. And given P threads, which index do we want to have on thread 0 to handle? So the question, as I said, there are the two ways. So we want to cache on CPU. So we want to have this index, the range index I mentioned before. Now we'll show you in Kokkos, must be continuous on CPUs. So for 0, 1 until n p, well, it must be strided for GPU. So we have to have this different behavior of the indexes in order to have cached threads on CPUs and coalesced on the GPU. So last, how it works on Kokkos. Kokkos index mapping and default layouts provide efficient access for if the iteration indexes correspond to the first index of array. So if you are giving if the first index of the array correspond to the iteration, it will be Kokkos that will take care of, giving, in case of CPU, a continuous index or a strided index. In most cases, I would say. So the layout will affect this index, so the range and the index, in order to minimize the cache misses. So to sum up this latest concept, every view has a layout. The set a compile time through a template parameter. The template, this template parameter can be used the default one, or you can specify another one. You can modify and create your layout. The most common are layout right and left. Views in our space are default to layout right, and views in CUDA space default to layout left. Layouts are extensible and flexible, and for performance reason, memory asset paths must result in caching on CPUs and coalescing on a GPU. Kokkos maps parallel working indices in a multidimensional array layout for personal and portable memory access. And all of what I explained in the last 5 minutes, there is not in OpenMP, OpenMC, OpenCL. So this concept of layouts and managing the index through layout is not available in OpenMP, OpenMC, and OpenCL. and you need multiple versions of code to address this or pay the performance penalty. So I will draft the conclusion. Probably I will draft the conclusion of what I explained this last hour and a half. So we have seen the importance of performance portability. So writing one code, but a code that could run efficiently on multiple architecture. The reason why we are currently using Kokkos, and probably in the future also much more people will use Kokkos. We will show you the basic parallel patterns to recall parallel for and reduction and advanced reductions. And I'll show you the Kokkos main concepts. So the range policy, the body of work and parallel pattern, then the execution space and memory space, the mirror view, and the layout.